Hello, everyone, and thank you for joining us for today's Climate Action webinar, Water Part 2, Design Approaches to Integration of Natural and Built Systems, created in partnership with the Climate Action Resilient Design Committee. AIA California recognizes that the planet is experiencing an urgent climate emergency and that California should continue to elevate its position as a global leader in addressing the grave challenges of advancing climate change. To help do this, AIA California has developed an in-depth educational climate action webinar series that incorporates the AIA Framework for Design Excellence and includes zero net carbon design education. To qualify for continuing education credit, AIA California provides learning objectives for every webinar and includes them in the PDF presentation that can be made available online. Few quick housekeeping reminders. Today's session is being recorded and will be posted on the AIA California website, www.aiacalifornia.org, along with any additional resources shortly after today's session. Today's session qualifies for 1.5 AIA HSW learning units for those watching live, and AIA California staff will report these units for you. Please use the Q&A function to ask any questions for today's presenters. You can also like a question to move it to the top of the queue. Questions that are not answered in the webinar can be made available on our website. I'd now like to introduce our moderator for today's webinar. Pauline Souza, FAIA and lead fellow, is co-chair of the AIA Climate Action Communications Committee and is the Director of Sustainability at WRNS Studios and has over 30 years of experience within the industry. Some notable projects from WRNS Studios include a straw bale visitor center for the U.S. Forest Service, Sacred Heart School's Stevens Net Zero Library, which is the first nationally certified net zero library in the country, the Sonoma Academy Janet Durgan Guild and Commons, which achieved LEED Platinum and is the first project to be awarded both zero carbon and PETAL certification by the International Living Future Institute, and our case study for today, the Microsoft campus in Silicon Valley, which recently received an AIA COTE Top 10 award. And now I will pass it over to Pauline to introduce the webinar.
Thank you, Sarah. And many of those projects that you mentioned were made better because of talent like John Lays, who will be our speaker today. Again, thank you, everyone. Hello, and thank you for joining today's program, The Water Part 2, Design Approaches to Integration of Natural and Built Systems. I've had the great fortune of working with incredible talent over the years, and John is absolutely one of the best, along with his firm Sherwood engineers. My advice to the architects in the room is find great consultants like John and listen and collaborate with them. Designers aspire to do the right thing when it comes to ensuring resilient outcomes for our projects, including the integration of water management into the design of a project and process. So how do we recognize and care for this resource? New challenges surrounding water management have materialized over the 20 years. Many of us in California will say maybe over the last 50 years. And solutions are requiring more sophisticated approaches to helping quantify benefits for clients, design partners, regulators, and the community. Many of you remember in 2014, the then state governor, Jerry Brown, declared a drought state of emergency, and that was just at about the time where we were working on the Microsoft project that John will share out. With a heavy focus on resiliency, Sherwood Design Engineers has refined the approach to water management to focus on the relationship of water and built and natural systems. I'd now like to introduce John Lays, PE and lead AP. He's a civil engineer leading sustainable infrastructure planning and project implementation at Sherwood Design Engineers. John is a managing principal of Sherwood's headquarters, their office in San Francisco, and he has over 20 years of experience working with institutions, public agencies, private developers, and folks like us on infrastructure, sustainable infrastructure systems. His extensive experience ranges from the development of statewide net positive water guidelines, like we did collaborate on in the Hawaii Department of Education, overseeing the design of net positive water campus for Microsoft in the Silicon Valley. And all of his projects, on all the projects, John pursues integrated water management strategies that achieve project design goals while strengthening regional natural systems. He is always in pursuit of what good looks like. So John, please take it away.
Thanks, Pauline. Really appreciate the introduction. Sarah, I'm going to switch the presentation here now to jump to the topic of for today. I don't have an agenda here, but essentially we're going to run through a little bit of an introduction to kind of our approach to design, some of the frameworks we use, and how we've kind of advanced our thinking of how we design with water resilience in mind, and then end on two case studies. The first one will be the Microsoft Silicon Valley campus, which opened about a year ago. And the second is UC Berkeley's Resilient Water Plan, which we wrapped up last fall for UC Berkeley. So I'm going to jump into things here. Again, Sherwood Design Engineers, just really quick, this is our 20th year as a firm. We've had a great opportunity to work with Pauline and many others over that period of time. And although we're technical civil engineers, we try to differentiate with an approach that really focuses on collaboration and working as a meaningful part of the design team, but also thinking about the vision, how we're bettering the community we work within, how we're bettering the design outcomes that architects and clients and all of us are striving for, and how we integrate the environment in our projects. So we really like to think that we're kind of changing the way civil engineering is performed. And I think we've seen a lot of that from a lot of different design disciplines in recent years. It's been a really exciting period of time. We really work as civil engineers on all aspects of projects. So although today we're going to be talking about a tech campus and a higher education campus, we work from single family residences, up to large planning for sites in regions and even countries at times. So jumping into it a little bit, it's interesting. There's obviously just been a lot of thought and work done on the topic of water for many decades. There's been a lot of great work that's been done recently. We pay attention to a lot of this. We use different metrics. We use different tools and approaches on different projects, depending on who the client is, where it's geographically located, what some of the outcomes are. But fundamentally, we firmly believe in what a lot of groups out there are really trying to do in terms of thinking and integrating water into their projects. And as I think we all know, context is everything, right? Where your project is everything. Oftentimes when it comes to water, it comes to design. So for any project, the water that's needed within terrestrial freshwater ecosystems will be different. The water that's needed for human consumption, for our facilities is different, and how you plan for a project kind of always comes back to understanding the water availability, the social environmental conditions you're in, and the place. We've also been incorporating a lot of thinking around circular economy into our projects, and really making sure that we're not thinking about kind of water for water's sake, right? Or water use for just the sake of reducing it, but also really trying to tie our work into environmental and socially regenerative applications. So really looking, again, context-based, how is our project context, local communities that we sit within, work within, and make sure that we're not, doing something that may be disruptive to somebody else or something else, for the end goal of of having a quote unquote sustainable outcome for our project. It's really interesting. We'll talk about this in a little bit more detail, but kind of understanding when to use municipal systems versus on-site systems for water management is kind of part and parcel to some of this thinking. The water balance is naturally circular, and again, I think one of the ways we differentiate our approach and what I want to leave you with today is really that, although a lot of times the topic of water is around what I'll call transactional water, the water that runs in our pipes, the water that we see when we turn on our faucet or flush our toilet or run our irrigation systems, the metered water that we can, most easily kind of calculate and provide a metric against. Just as important or more important is the water that moves through our natural systems. So it's where does our stormwater go? Are we recharging it? Where does our wastewater go? Can it have a restorative impact on the environment we're within? What happens to our soils as we build and develop and cut off their access to moisture? That whole side, which I call the wild water side of things, is just as critical to think about. And what we've really kind of seen in recent years is that the scales, the scale is important. There's been obviously, most developed countries invested just a lot of energy into centralized systems, and they make sense, and they work, and we need to continue, to develop them, for our new communities. But there are obviously a lot of other scales to think about and work with. And when we talk about and think about resilience, and we think about kind of some of the challenges we have ahead and some of the locations that we work, again, coming back to context, it's not always the right solution, to tie into that municipal system. One great example is kind of what happened during Superstorm Sandy. The Bay Area, most places are the same way. Our wastewater treatment plants end up at the low points, right, close to the coast, close to the bay, where they can treat the water and then outfall it. They'll work by gravity. Well, during that storm, a lot of wastewater treatment plants went down and were impacted. And if you look at the smaller community-based systems that were up and down the coast of New York and New Jersey, they by and large did not. They were able to maintain operation. They didn't pollute into the natural environment, during the storms. And so we know, there's a time and a place for decentralized. There's a way that decentralized infrastructure, can work with larger centralized systems and, support each other, and work together. And that's a lot of, what our work is in thinking is really, again, thinking about your context, whether it's a single building site or a campus, or a city. What's the right solution for you? How do you plug in to both the natural systems and built systems that you find yourself surrounded by? Again, there's just been so much work done there in this area, to date and over the last few decades. But here in the Bay Area, critical to our work is is oftentimes, the jurisdictions we're falling within, San Francisco Public Utilities Commission, Santa Clara Valley Water District down in the South Bay, and really understanding what their goals and priorities are, so that as we're developing, projects that may not be kind of business as usual, we can fit the thinking into their goals, and we can kind of leverage things they're trying to do. This especially, we're going to talk about this on Microsoft a bit, but it's we're intentionally, we shall be intentionally, pushing the envelope when we can improve, conditions, either the local ecological conditions as we're managing stormwater, or the water resources when we're thinking about things like on-site reuse for reasons of sustainability or resilience, or diversifying water supplies, and those sorts of things. So again, it's kind of important that for any project as you get started, to really, again, do the research to understand the watershed you're in, contact those groups that have done a lot of work already around understanding kind of the watershed and the water resource and the water management kind of strategy for a region, and really take that into account as you begin the design process. I've made this notion toward on-site reuse a few times so far in the conversation, and Sherwood has definitely done a lot of work over the last 2 decades in this area, and it's I'll be the first to say it's not the right solution for every project by any means, but we find that there's a lot of scales where it makes sense, and there's a lot of places where it makes sense as well, based on kind of that location's water resources situation. So we see at the right scale that you can avoid costs. You can do things that really kind of help a project have access to more water for irrigation, which is great when you're thinking about having a more robust landscape, being able to provide more habitat, sequester more carbon, reduce urban heat island effects. And the value that you see in terms of kind of having these resilient systems, oftentimes more than offsets the cost of having more fragile centralized systems. We also really are a firm that believes in expediting innovation, and we in this notion of in the future having this conglomerate of if you will, of centralized and decentralized infrastructure that's really working together. These types of systems at these scales, like we'll talk about in the case studies, are great ways to push, really. So obviously it's been exciting for us over the last number of years, in some ways, as we've advanced work in the water world. There are a lot of resource flows that are out there that are critically important, and that our sustainable buildings focus a lot of time and energy on. Carbon is at the center. Carbon is arguably the most important thing for us all to pay attention to. But water is clearly a big one, and touches many aspects of a site. It flows through the pipes of a building, like I've mentioned, but it also really, and I'll consider that kind of resource sustainability and how we use water. But a lot of what you see with water in a site in design is what you're thinking about out on the site. you know, the big storms, and with climate change, the increasing in intensities and how we're handling the runoff rates and flooding issues, the quality of the water that we're releasing from our sites, putting back into the natural environment. You know, how we're sequestering carbon, how we're thinking about water as a key player in fire resilience, both with gray infrastructure systems as well as green infrastructure systems, and then its integration, you know, with energy and resource recovery. So water becomes, especially as the climate heats up and things dry out, it becomes, you know, one of those resources that that really moves kind of across the spectrum of the site from inside and outside. And again, it's just as important to be thinking about the water, the wild water that flows without the site, as the water within. You know, a big piece of this then becomes what most of us, you know, term stormwater, and really getting that stormwater kind of back into the water cycle is critical. And it's not just treating and releasing the stormwater. I feel like a lot of projects these days really start to look at stormwater as transactional. How many square feet do I need for my bioretention basin, right? Where am I going to fit that? Am I going to line that? Is that going to be, you know, lined in concrete and tucked up against the building? Kind of where is it going to be? And it's turned into, in a lot of projects, kind of more of a calculation and a transaction. I got to treat the water, then I got to release it to the system so it can go into the pipe. Hey, it's clean, so the world's better. Hey, I've detained it, you know, so I'm not going to cause downstream flooding. Great, but you're depriving the local ecology. You're depriving the environment of water that once went into the ground. So we have to, you know, I think also move from thinking about stormwater as kind of a transaction, but more of an asset in a different way, in a different guise, right? It's more about how do I get the stormwater to flow across a landscape and then into a bioretention basin, right? As opposed to, you know, just a treat and release. And this kind of brings us to what, you know, a lot of us have been talking about and thinking about in recent years, and how stormwater code has developed within the Bay Area and throughout the state, of really focusing on, you know, returning our kind of, I'll call our typical site conditions of today. A lot of the sites we're all working on are redevelopments, right, of old office parks or infill projects that were once parking lots and are now turning into multifamily housing, you know, whatever they may be, but they're very impervious. And how we not just kind of treat and release that water, but actually try to restore what I'll call the eco-hydrological water balance of a site is of utmost importance. I know there's a lot of things in the chat. Pauline, you'll jump in if there's any questions, I guess. I just looked at the chat. It doesn't look like they're real questions. It's just more informational stuff that I can tell.
Keep going,
okay.
John.
Okay. So I'll keep going. Adoption of resilient design. So I want to talk just a little bit here about our kind of resilient water approach, if you will. So I think it all starts with our principles, and let's talk about it from a project standpoint. You know, so I think we can all, you know, agree that there's a lot of typical principles out there around conserving, protecting, replenishing. You know, but we should all just continue to challenge ourselves and our clients to think about resilience, to think about how water integrates into the landscape or integrates with energy systems, right? And we should make our projects and think about our projects in a way where they're educational and they educate, they grab people's interests, right? They have an opportunity in a way to educate. and they're restorative in nature. It's going to take 100 to 200 years to kind of change the curve. We only get to develop a site every 50 years or 75 years or something like that. So we really have to take the opportunity on every site we have to think about, water in that context. The second, element then is what I'll call our framework. And, this is the organizational structure, that we talk in, which I mentioned earlier, which is really thinking about the natural systems and the wild water that moves within it, and then the transactional water within the built systems, right? So we kind of end up looking at projects with those two lenses, and then obviously there's a heavy integration there in a way that these two water networks, water systems, I guess, if you will, work together. Looking at it pictorially in a kind of a section view, a lot of us work in these, in these environs where we're touching, natural ecology on one side, as we build up against a stream, right? Or on the Microsoft project, we're building up against Stevens Creek and a habitat overlay zone. So there's a kind of a real opportunity to kind of think about that area, and then how the wild water and that transactional water that's happening kind of within the buildings and where the public realm, are working together. There's a real important emphasis also, we think, on kind of wellness and on kind of the community and the benefits that come to all of us as inhabitants, having a real emphasis on the habitat and ecological systems, as well as the more specific water systems. We'll talk about this again as we get into the Microsoft project, because it was really a kind of a fascinating approach there, where it all started from the individual and the employee and kind of built from there. So this really needs to be a piece that's of utmost importance in all our work, really thinking about not just the ecological health and the water sustainability, but also human health and us inhabitants that live within it. And so oftentimes our work breaks down something like this, where we have kind of the built systems elements that go into what I'll call a sustainable water framework, and there's a number of standards and guidelines and projects that support that, as well as on the natural systems side, something similar. So that's kind of how we approach it with our two main frameworks. And then what we find, and kind of was at the bottom of the previous page, is that it's often helpful and and critical in terms of really making a difference, is really trying to come up with some key projects that really make the project succeed and really make it do what your aspiration is, what you're hoping you can get out of it. And this can show up in a lot of different ways, and you'll see that on some of the project case studies that we get into. Especially at UC Berkeley, there's a whole slew of kind of what we call catalytic projects. So these can be something like, hey, let's really focus on that stream and riparian buffer edge and how we're going to restore it and integrate kind of the human and community uses, the stormwater management, right, as well as restoring the banks, building out the riparian buffer so it keeps the stream cooler with shading, and all those things can help in elements of resilience, flooding, urban heat island mitigation, etc. And then on the kind of, I'll call it the transactional water side, there's been just a lot of advances done in water conservation and reducing the water we use, but ultimately, if you don't get into a reuse scenario, you end up getting to 20, 30, 40% reduction from baseline, or from maybe what you call a typical project. So we spent kind of a lot of time at looking at kind of water reuse facilities. They can be as simple as small scale residential rainwater or gray water laundry to landscape systems, or in the case of these, some of these images, multifamily housing projects or university projects. And they again, have a lot of overlap with some of our other resources such as energy and waste, and provide a lot of opportunity within the guise of sustainability and resilience. So the main tool we use here is the water balance tool. I know probably everyone on the call has seen a water balance. They come in all kinds of shapes and sizes. We tend to, again, pull the natural systems aside and the more transactional systems below. But we have a real process for accounting and thinking about metrics on the natural system side as well. So there are ways to calculate kind of how much water should go back into the soil to keep the moisture at the levels that it should have, or what should your site infiltrate if it's possible into the ground. So kind of thinking even quantitatively through the natural system side is an important component of working through a water balance. And I know this is maybe a lot. I'm going to break it up into a couple slides here, but we again then really think about it in terms of this eco-hydrological water balance of the natural systems and all the inputs and outputs, as well as the kind of the transactional or metered water balance, which is more tends to be within the buildings. And there's integration, and we work with them together. So oftentimes we'll see recycled water as an important input into the natural systems, and helping with things like groundwater recharge or environmental flows, or the water for plants to transpire, right? Water to keep soils moist so they can continue to work their magic, and keep the connectivity between all the living plants and trees moving. And I guess I had one, and I think I talked about a number of these, I guess. Sorry, I forgot I have this slide here. But so a little bit maybe of a vision, if you will, or an opportunity overlay. But again, some of those key things we think about in that water balance, really protecting and restoring, or protecting existing habitat, continue to restoring, using water to build soils back up. In so many of the places we work, soils have just been thrashed, if you will. They've been diminished. They're not seeing the organics go back into them. There's a lot of work to do in terms of building our soil base back up, which supports the plant life that we all depend on. And then really focusing on natural system linkages and integrating BMPs and stormwater BMPs in a kind of a thoughtful way that's supporting of these natural systems. That's one key thing I'll say about stormwater. It's like we really do need to think about it as a support role. It's an opportunity, right? It's an opportunity to support all these things that we're talking about. And then on the flip side, we have the transactional water balance, where precipitation often plays an important input, because that can be a water resource on our projects, most typically for things like irrigation or, or toilet flushing. So I'm not going to belabor this, but, on a water balance, we're looking at the demand side, and, these are by no stretch all the demands that are considered on a project, and likewise supplies. And what's, really always really important is to look at water balance at either a daily or monthly time step. We typically run everything at a daily time step, and then kind of look at them on a month basis, and not on an average year, if you will, but on a representative year. So especially when you're looking at rainfall and storm, it's best to choose like 1984. Try to choose a representative rainfall year that meets in total aggregate some of your typical averages, but it's more realistic in terms of kind of when the rain is falling and how much is falling on a given day, because it's as we all know, rainfall and precipitation is never typical, and it's getting more and more wacky, if you will, every year. But in California, we always find ourselves in an imbalance. We have these dry summers and these sometimes wet winters, and it's really important to look at how our demands, shown in the bars, start to change through the course of the year. You see irrigation in green, picking up, and you see in this case potable water with potable water demands going down in the summer. I believe this one specifically is from a university campus, where oftentimes you will see reduced potable and non-potable demands through the summertime. And then you'll be able to again look at kind of like your black water resource and kind of the more brownish color, I guess, at the bottom, and then your potential for gray water second to that, and then your storm and rain. And we differentiate those by, rain is really what falls on the roofs. Storm water is what falls on the site itself. And, gray water can be, can definitely be a resource. We see a lot of gray water projects on kind of residential buildings, where if you treated all the wastewater within the building, it would be way too much. And so you can downsize some of your infrastructure investment if you're just taking gray water from a portion of the building and meet your toilet flushing and irrigation demands from that. Or we see a lot of gray water at more the residential scale or single site scale. We never see kind of a gray water at a kind of a larger campus scale. It's much more efficient to just blend your wastewaters into one wastewater, and just work with one conveyance and collection system and one treatment system. And then kind of maybe finally on the water budget, we get into, when we're thinking about reuse, we always get into kind of the cost benefit. It's not a small proposition to take on a reuse system. So we're always advising clients to really understand what you're getting into, understand the capital costs, the OpEx costs, and importantly the kind of the labor hours, right, or the time it takes to manage the system. So it's like any kind of central utility plant type infrastructure. When you get into water reuse, it really is a system that you got to pay attention to. But the case can be made, and we'll talk about that in a little bit of a second here. Yeah, so just bringing back this slide to once more just kind of look at the distinct flows, and then I wanted to just, before we jump into the case studies, build for a moment on kind of the reuse side of things. We did some work with Doug Farr a couple years ago in his latest book, Sustainable Nation, where we really started to look more closely at some of the metrics around water reuse. This is just always one of those questions that comes up on projects. Does it make sense to treat and reuse water, especially wastewater, as we're getting into kind of larger residential projects or community-based projects, campus projects. And so there's some good rules of thumb, out there. And a lot of it comes down to obviously scale, but two, the cost of water and sewer services in your local community. So if you have a relatively small project, 25,000 gallons per day project, so kind of the size of the Microsoft campus, about that we'll talk about. If your sewer and water fees are adding up to $15 per thousand gallons, you'll look out at that over the lifetime of a project, and it'll have a positive return for you. And then as you get into a bigger project, 100,000 gallons, UC Berkeley, which I'll talk about, was closer to, I think, 400,000. You can really make those work affordably if your water and sewer fees are, down as low as $10 per thousand gallon, and kind of go to the MGD, a million gallon per day size. It's, obviously more favorable. This may be just a couple years out of date, but this was a snapshot of combined water and sewer rates per thousand gallons in a lot of the communities across, across the U.S. Atlanta's just off the charts. San Francisco is a bit over that $15, but this is one of those, metrics we look at and think about as to a new community to work with and try to use the rule of thumb. Hey, if you're at about 25,000 gallons a day, we can maybe make it work. If you're a bigger project and you're up closer to 100,000 gallons a day, you can actually entertain third-party financing if you'd like, and have a design, build, operate, maintain entity come in, design, build, operate, maintain that system for you, and just kind of do a great, potentially a great sustainable move, again depending on your context, for no additional capital. And that's the type of thing that Emory University did, for example, with their water hub, is really partner with a third party who came in and took on the risk associated with the costs and the permitting and the operations, left them with a good situation in terms of the amount of water they were able to reuse on that campus. I would caveat it when you're kind of thinking about larger scale water reuse systems for your projects, that when it's a speculative, kind of more developer backed project, there's less opportunity. But really when there's kind of larger institution projects with just a known demand, something that's predictable, that's really where the opportunities tend to stand out. And then in that book we looked at kind of all kinds of metrics in terms of kind of water infrastructure, and this was just kind of one example where we were comparing different typologies and looking at cost and space implications and energy use and things like that. So we've done a lot of work on these types of metrics over the years to just help make decisions really quickly about what might make sense for a project and what might not. Okay, so we're going to jump into a couple case studies. Yeah.
John, I know we said we would hold questions till the end, but maybe just to give you a chance to drink some water. There's a couple of high-level ones that maybe would be great for you to comment on. One from Stephanie. The question is, decentralized infrastructure seems to be more resilient. What is the impact of creating a satellite water system on site? And for smaller urban infill sites, can it be possible to include, or are the spatial requirements too challenging? So just sort of thinking about it from a planning standpoint and an approach on decentralized or combined.
Yeah, no, it's a really good question. Whoops, sorry, I was trying to minimize question. It's a really good question. We think about this a lot. In that last tool I just showed there, kind of helps think about it spatially, because it takes space, right? And if you're on a tighter site, you really have to think about where that goes. Is it down in a basement? Is it in a mechanical room? How big is that mechanical room? How are you getting access in there for O&M activities? So what we tend to see is kind of on the in-building systems, you're really trying to make as small a footprint as possible, and you're trying to just minimize it. So you're tending to use more membrane type treatment systems rather than maybe natural systems for example. In terms of resilience, they can be more resilient if if they're designed right and thought about right and put together right. If you're in a small building and there's some kind of event, if your system is relying on electricity that's provided by the grid and you lose that electricity, then kind of all bets are off. But if you have a system that also has backup power, for example, or the power doesn't go out, for example, right? Then you're there with a water supply that others may not have and could benefit your site and your neighbors and local community as well. We tend to, we do a lot of work, I think a little bit at more like the district scale, right? So once you're starting to get into a multifamily housing type situation or a campus system, and then again, a lot of the campuses we're working on, you end up looking at 20,000 square feet of space, right? It's a big area. And if you're in the bottom of a multifamily residential building, you're looking at a couple thousand, square feet of space. So it's real. Right. It is a real space constraint that you gotta think through.
Kind of still case by case, and with all the other factors in play. So great. There are a good set coming through, but we'll let you go through the case studies, and then we can come back to some of these questions.
Okay. That sounds great. So I'm going to jump into Silicon Valley campus, Microsoft's redevelopment there first. Just caveat it by saying Pauline would do a much better presentation on this than I would. She knows this project inside and out and loves it. But we worked tirelessly together for multiple years on this project, and it was a lot of fun. And there was a lot that this project did. Each of these areas, thumbnails, I guess, are kind of important things to talk about and have stories behind them and kind of tie together and integrate. And we're really considered as critical. We're going to talk today, we're going to touch on the campus planning and then really talk about water and habitat, right? Where the transactional and wild water systems, came together, and talk about their story on the project. But there's a lot, it goes a lot deeper, than that. Microsoft's office was kind of your typical suburban office park, surrounded with parking on all sides, 5 separate buildings that housed 5 separate kind of groups that kind of did their own thing, and disconnected, from each other. And the vision was really try to turn that into an integrated campus, really restore the Stevens Creek riparian zone, which in Mountain View is a habitat overlay zone, really provide an opportunity for that kind of habitat to roll into the campus and even up onto the roofs. It's only a two-story facility, so really the height of the facility has come down quite a bit from where we see a lot of campuses, and that made it, I think, a lot more opportunities and really intriguing, as well as a lot of I'm sure code challenges and things like that. Where we're sitting here, gosh, I don't have like a even further out zoom, but this is the city of Mountain View with the Highway 101 coming through on the south end of the bay in San Jose, and in Mountain View. And I do have a laser pointer. So like, Google's land holdings and the Googleplex, sit just a little bit to our northwest. And the Microsoft campus is kind of right at this very interesting intersection of, Stevens Creek moving north-south and the, Highway 101 east-west. Some of the real challenges that I alluded to were just, the way people moved and collaborated or didn't. And Microsoft had a lot of intention around trying to attract and retain the best talent, and kind of really do something that was both right for their employees and right for for the greater community and the natural systems in the planet. So a lot of time was definitely kind of spent up front working through kind of overarching goals for the project. But what was really interesting is kind of where it all started at the human scale. The campus design was envisioned first with kind of how people work, what do they need, not just in terms of kind of their jobs and how they get their work done, but also as individuals, what do we need to be healthy and kind of thrive personally, and professionally within the environment. And so a lot of thought went into kind of the various scales, if you will, of an office campus and what happens kind of at those. And this notion of, or this intentioned design toward these quadrants was developed over, gosh, probably a period of 4 to 6 months, through a lot of user meetings and a lot of really work for the architects, really working to understand the best way to put this together and to give the most flexibility. And so these quadrants which really added a lot of flexibility in terms of people being able to work isolated or in small clusters or in bigger groups and continually kind of transform their working environment all the time, having access to indoor-outdoor environments, stairs, kind of all through the campus, which I'll show later, almost turned into a labyrinth, accessed by this amazing green roof on the surface or on the roof. Some of the core sustainability objectives, around habitat, water, energy, and of course the kind of the well-being, of the employees was, brought first and foremost. And I think Microsoft outdid themselves in terms of pursuing and achieving LEED Platinum. I think pulling 98 points or 96 points. Really remarkable. Living building challenge and the well building standard. So kind of how those quads laid out on the site. Something like this. where you get 4 of them in a cluster, stacked, obviously in 2 stories. It's flattened here, and then that's connected by support space and the like throughout. And a real intention around visitors and others that will come to the site, for conferences or expositions or other things, and how they move through it as well. So diving into, I think, water more specifically than, water from the outset was just like Pauline mentioned, we were just in this time of almost crisis, and so it rose to the forefront, and so we spent a lot of time looking at it up front and understanding some of the challenges around water scarcity, and Microsoft really latched onto it as an important, one of the key drivers around sustainability for them, and so very thoughtfully we worked with them to develop metrics around these for the project, and integrated into the design. But it was related to, I think, more on the resilience side. The site was really interesting in terms of its location and some of the risks that we were thinking through, not just the drought and the challenges we were seeing, but longer term sea level rise, potential impacts. We're sitting partially on a plume, and we have some contamination to kind of think through locally. We're adjacent to Stevens Creek, and really understanding the quality of the water we would either be putting into the ground for our plants, or putting discharging back out to supplement the creek's base flow were important. And of course, along with sea level rise, the opportunity for changing soil conditions. So our water balance analysis really started at that kind of overarching supply and demand side, and we thought through how we would approach a net zero water project in the context of living building challenge and the day-to-day operations of Microsoft. On our supply side, we really had kind of all our treated wastewater that would come from the potable uses and the flushing of toilets, as well as the rainwater that would fall on the roofs. And we matched that with a strategy of use, obviously to flush toilets, but also to support quite an extensive landscape. And as we looked at that water balance, again, kind of over the course of the year, we saw a couple things which are typical in California in terms of the dry summers, especially down in Silicon Valley, where the rainfall is, 11-12 inches a year, and the summertime temperatures are really high. And developed a strategy around, in the winter, you're really storing excess non-potable water, so that's a really important part. But you're also really focused on kind of hydrating the soils, and we spent a lot of time with our horticulturalists and landscape architects, thinking through what would happen, what happens in the natural conditions in California, right? In natural conditions, plants don't get a drip irrigation system, irrigating the top, few inches of the soil 3 times a week or something, right? In California, we get big rainfall events. It'll rain for a couple days at a time, and that water will really hydrate the soils. It'll really infiltrate, kind of deep into the soils. And our native plants, they grow deep roots that follow that moisture down as the top dries out and waits for that next rainstorm 2 weeks later. So we set up this system of deep irrigation during the winter months, where every week or two, kind of mimicking again a kind of a typical California rain year, we would go in and really kind of hydrate the soils down to a lower level, and that became kind of a strategy on the water balance side, and on the ecology, side, to really try to restore, the soils, which, have been covered primarily by, concrete for, and asphalt for so many years. So a little bit on, our rainwater strategy, which is just really on the kind of the gray roofs. We had an extensive green roof system, so stormwater that landed on green roof system or the site was really directed back into the local ecology, and all our black water or wastewater was essentially looped. Early on, we cut out all water associated with cooling. There's a whole energy story as well around, and that's part of that. And we spent kind of a lot of time through the design cycle working as an integrated team to continue to refine storage capacities, landscape areas and irrigation demands, the roofs we were harvesting from, and how that infrastructure was working, to really develop, a system that would be right sized and kind of meet the needs. So really quickly, on the process flow diagram, municipal going to potable with heavy conservation, rainwater, its own separate treatment and storage, along with an on-site wastewater treatment plant. Those would be blended together for use as both irrigation and indoor, non-potable uses, toilet flushing. City of Mountain View did require us to have, backup recycled water and a, municipal sewer overflow. And the recycled water, I think we're going to find is helpful here as we go through our landscape establishment period. And then, finally, the stormwater, really went to, it went through treatment and then ultimately ended up in the, restored riparian edge, a series of willow sossels along the creek. This is a little bit of a schematic that shows kind of the rainwater and stormwater flows. I'm going to move. I'm not going to stop and kind of walk through it all, but you can see spatially some of those systems I started to talk about in terms of the areas of the roofs that were, draining to some of the cisterns, as well as that Stevens Creek area in green out to the edge. We ended up kind of sewering the project out to the low point of the site, and then from there, kind of pumping it back to the on-site wastewater treatment plant. And the design of that plant was really, was really interesting. So near our low point, we had our influent pump station, and one of the things that we spent a lot of time talking about is, how do we make the wastewater treatment system integrated in a kind of a visual and compelling way as well. This happened with the energy system as well. I mean, when you drive by the 101 and you look over at the Microsoft building, you'll see the parking garage, and you'll see these blue energy storage tanks that just protrude up out of the the parking garage. So we spent a lot of time as a design team to make sure these elements were integrated. And so we ended up citing a lot of these systems kind of within the edge of the building and the open space, including a primary treatment tank, a series of secondary tanks, and then finally a vertical flow, wetland, which I apologize. I have some recent photos, but I didn't get them into this presentation quite yet. When you're out there on site, suffices to say, you would kind of never know it was a wastewater treatment plant. You see it as elements kind of integrated into the design with planting, and then some signage and some kind of grayer infrastructure elements that I think allude you to what's going on. And finally, back into the parking garage, you have the final tertiary filtration before it's boosted out to the system. I get these are just a couple construction shots. Again, apologize, don't have some of the finished, but we had I think 400,000 gallons of rainwater storage. So we built these kind of large, I think 20-foot diameter Xerxes tanks up against the edge of the garage. And this was partially buried, and then backfilled that to kind of create this upland area within the project that I'll talk about a little bit in the habitat side of things. So in the end, although the occupants are increasing and we have 3 times as much landscape, we're planning to see, quite a reduction from current water use. We're about a year in right now, so we're getting ready to kind of commission, if you will, our first year on living building challenge. Don't quite have kind of the stats yet. We anticipate upwards of a 5-year, plant establishment period where we'll be utilizing some of the city's recycled water to augment the irrigation before we get to that net zero water goal, that the campus has committed to. Okay, then on habitat, I'm just doing a time check. We have about 22 minutes left, right?
Right, I was just gonna say, yeah.
Okay, maybe spent a little long on some of the earlier stuff, but on the habitat side, really important was understanding the historical context and where the site sat, because this relates to some of the existing soil conditions we see out there today and some of the opportunities for what will work especially given the groundwater elevations that are below us. So on the top section, what historically was through here, a lot of wet meadow and some willow groves. The Microsoft campus was on this little bit of this knoll that provided a slightly different opportunity than some of the sites around us. But over time, there's obviously in the middle section just kind of a lot of fill and office and light industry development. And so we've really tried to kind of with this design bring back a lot of the function that was once there and introduce some of the habitat types that would have been in this, been right in this area and still exist in kind of the greater region. So importantly was our connection to Stevens Creek and how to really kind of restore that riparian edge. And we think a lot about kind of how creeks and rivers work and the importance of base flow and the importance of kind of keeping the surrounding areas hydrated. And so that was kind of a very important element, as well as the species that move through this area and how we're creating that habitat overlay for them to use successfully. And it's neat. I was up on the roof a couple months ago, and there's just a lot of activity up there from like a plant and animal or insect standpoint, primarily birds, butterflies, insects. It kind of blew me away that this once very kind of dry and hot campus environment really has succeeded in that connection to Stevens Creek and dragging, if you will, that the natural systems within the creek up into the campus and into the the buildings and roofs. And this is just an illustrative. I apologize again, I wasn't able to pull in some of the more recent photos. So maybe I'll pause there, Pauline, just for a quick second. We have about 20 minutes left, and we have UC Berkeley to still go through. So I might have to move relatively quickly through UC Berkeley, but I also want to afford a little time for Q&A.
Sure. There are, let's see, there's some higher level questions. I think you answered them in your presentation, but do you want me to? One of them has to do with the ratio of wastewater to reclaimed water. I think you talked about that in that last slide regarding the economics of it. I think if you can get through the Berkeley case study in maybe 8-10 minutes, John, we can kind of go over some questions on how to calculate it. Maybe also some capacity challenges, and maybe how you've worked to move clients along and integrated it into the project. Is that reasonable?
Yeah, let's, I'll just apologize ahead of time that I won't be able to spend as much time as I would have hoped on some of these elements, but let's jump into it. Over the last 4 or 5 years, you see Berkeley has been working to update their campus master plan and long-range development plan, and we were part of the team led by Sasaki to do that. A couple of kind of the key, the key big ideas that came out of that were trying to restore the glade, really celebrate that as a big move that Olmsted had brought to the campus, thinking about Strawberry Creek, discovering innovation, really focusing on campus life and that intersection with Bancroft, if you will, and making the campus more cohesive and heavy focus on mobility. We, as part of the campus master plan process, developed a resilient water plan set up in the framework that I talked about earlier. There's a little typing on the background, so Sarah, I'm not sure if you can mute everybody else for me. I'd appreciate that. Broken up again on the sustainable water side, which really looked at kind of the water flows themselves, the transactional water that's metered in pipes, and then on the wild water side, stormwater and green infrastructure. Berkeley was challenged by its growth, because although it's not adding a lot of students, it's adding a lot of on-site housing. And if you understand the UCOP requirements for water use, it's all based on the campus user. Let me see. I'm still getting a lot of typing. Maybe we could just mute. Thank you.
That was me. Sorry, John.
Oh, no problem. And so what we saw is, although Berkeley's been really meeting the requirements around water reduction, they're gonna get into a real challenge moving forward when you think about the number of new students that are housed on campus and some of the water requirements of their central utility plants going forward. So we set up kind of a series of approaches, and spent a lot of time working through conservation. So really working to understand the high water users on campus, developing a set of standards and guidelines for them, and then knowing that they can't implement overnight, developing incentives in a plan to implement water efficiency projects over time. So kind of digging deep into the campus, really understanding which buildings, primarily wet labs, are the big building users, and then developing a program with Cal that they can implement to work through those labs over time to change out equipment and begin sub-metering and doing a fixture and equipment efficiency over time. They had kind of been thinking about turf replacement and have done turf replacement over time. So another big emphasis of the master plan was continuing to expand that approach and really trying to narrow the turf down to the places where it's used by the students or has a historical and design element. And then on the water reuse side, what we kind of saw is that conservation alone would not meet Berkeley's sustainability goals and UCOP's requirements. So we spent time kind of studying what are the water reuse opportunities at Cal, set some standards and guidelines around that, and then developed kind of our catalytic project. So a water reuse system was proposed in the site of the Dwinelle Lawn, with a distribution network that primarily feeds out to some of the key nodal plants where kind of the high water demands will be in the near term, as well as irrigation for some of the key lawns. And then, kind of thought long term about over the next 100 years as new buildings come on board or buildings are renovated, how they can be added to that system. Siting of a facility like this, there's a lot to take into account at a campus like Berkeley that's been around for so long. So there's quite a bit of time evaluating a number of different sites based on a number of different criteria to come up with the one that kind of made the most sense for the project. And the Dwinelle Lawn, the campus isn't a really interesting site, and part of the reasons the university landed there was just the opportunity for kind of education. They didn't want it to be something that was kind of in the background, hidden with the central utility plant, but really more something that could be kind of celebrated and used for academics and research and education as well. We developed a pretty comprehensive life cycle cost assessment to strategize when this facility would come online, and looked at net present value of a system like this and payback period, based on some assumptions around the ever increasing cost of water and sewer. So conservatively, when you look out 30 years, the net present value would be just over 8 million. But if water and sewer rates continue to increase as they are, it could be upwards of 80 million. And then on the kind of the wild water side, it was a heavy focus on kind of green infrastructure and natural systems. It started with zooming out and really understanding the watershed, the soils, the groundwater, where are we in the bay, and how are the systems working. We studied some of the challenges that the university is undertaking right now, or going through right now, and thought about how we can improve some of these conditions, with a plan to achieve multiple benefits. One of those being, being flood risk. It's something we've seen kind of just happen more and more at campuses as damage due to flooding because of just freak occurrences or lack of maintenance in the such or in the like. So the stormwater and green infrastructure, really thought about flood risk, storm drain conveyance, vulnerability to campus growth and climate change. So we spent a bit of time, working on, how the intensities are going to change over time and what that would mean for flood risk on the campus. And then, because UC Berkeley regulates it itself, we developed a new regulatory framework with them, and parcel with the local water board to kind of move them away from, again, a transactional, site by site, C3 compliance or stormwater management compliance for the campus, and instead a larger green infrastructure, framework that can be multi-benefit. So, we developed a framework that also ties into the regulatory requirements, and has a way of kind of tracking some of the larger, more impactful credits against some of the upcoming and in design buildings, that are really challenged from a site perspective, that may otherwise need to develop a small scale rainwater harvesting system to meet local requirements or, really constrained, flow through planters, we developed a system where it could really look at it from a multi-benefit, perspective. So I'm gonna skip ahead to kind of what that framework started to look like. Essentially there were 4 main typologies that arose, and I'll talk about kind of each of them one by one. The creek interface, the upstream tributaries, the connectors, and the north-south and the east-west connectors. So the creek interface, Strawberry Creek is just such a lifeline for the campus in a lot of different ways. And we specifically targeted a few areas where there's a certain amount of degradation and opportunity. And so identified a few places where we could restore natural function, improve flooding resilience, and really bring people more meaningfully to the creek. The upstream tributaries, when we thought through those, it was really areas where you have kind of large watersheds draining to a specific outfall into the creek, and it provided an opportunity for kind of a larger facility to be designed and constructed that could be done in association with a landscape project or a mobility project or something else, but that would really treat kind of a larger watershed all in one place. And then the north-south green contours, as we call them, are these kind of key transportation routes through the campus that peds and bikes go on. And if you know the Berkeley campus, there's just kind of a gentle cross slope across most of it. It steepens up as you go east. But we really saw these areas as contour swales, if you will, areas where we could pause water and treat it and infiltrate it along a longer contour, essentially. And then the sloped connectors are really areas where we saw just a lot of opportunity or potential opportunity for some flooding and some damage to buildings based on how existing grades were set, and existing doors and buildings and whatnot. So we wanted to make sure, because we've been seeing this in more and more campuses with flooding happening, that UC Berkeley wouldn't have an issue in the event of a larger than anticipated storm event or clogging in a storm drain or something like that they get flooding in a basement or a ground floor of a building. So we set up a plan for them for overland release through some of these key watersheds. I'm going to keep moving. And so this turned into a number of catalytic projects that are in various levels of design. And one of them is at the West Oval Glade, and kind of thinking through kind of a restorative approach to that. And so this is a little bit more of a diagram that's kind of functional in nature to show some of the water systems. Doesn't have all the kind of landscape and ecology in it, but it essentially has some bioretention and retention facilities on the kind of outer edge of the riparian zone, and then proposes a water quality channel that can take base flows off of the creek, or some amount of base flows, treat it, because all this water is coming from urbanized North Berkeley before putting it back into the creek. And for all these BMPs, we did kind of calculations following water board requirements around pollutant removal and kind of what that benefit would be to the greater community, and how Berkeley can kind of leverage those as credits, while also providing these kind of integrated benefits to the community. Then a little bit of an overlay on some of the opportunities that we saw in terms of, obviously areas for outdoor classrooms and learning, and circulation enhancements through this area. So Pauline, that's it. I know we're running short on.
That was great. No, that was beautiful, and I think it is And we've learned this through our work with you and your teams. It's important to sort of think big, the importance of place, to go out and in, to zoom in and zoom out, and to think about what can you do to do better. I think you've proven through a lot of your work that it's not about adding money, but it's about thinking through the systems and reaching out, and what could those what can improve what you have beyond the building limit. So there are a couple questions that I hope we can squeeze in, but a reminder that if we don't get to them all, we will, John has agreed to collect them, and we will share them out through the AIA. There is an early question about can you share, and there's three, John, so sort of time it in a minute. Any Southern California examples, and maybe any that you can just share out as examples of what you're presenting today, of how you're presenting today.
Like projects in Southern California? Or?
Yeah, LA specifically, or Southern, yeah.
Yeah, I mean, there is a lot going on in LA right now, especially kind of around the LA River, and some of the thinking around the integration of resilience to flooding, but also treatment of water, creation of community, and access to nature, and kind of restoration of it. It is a really amazing, I think, opportunity. We've just always thought about it as flood control, and the more we realize that the water starts in the in the headwaters, in the higher up in the watershed, and if you add a sophistication to how you think about managing water, including all your green infrastructure, right, and decentralized systems, and then looking for some of these bigger opportunities to take water out of the river and run them through wetlands, which has already been proven to work down there. I think we're going to see a transformation over the next decade or two of the whole LA River corridor and integration into parks and other spaces. The universities down there, we've done work at UCLA, UC Riverside, UC Irvine. They're embracing kind of some of that thinking as well. So I expect to see more and more at that scale. And then there's a number of large parks, like Orange County Great Park, which has a large stormwater harvesting program. So kind of really thinking about in LA, it's less about the rain that you get on a roof and more about the stormwater you get in a watershed. So I think you're going to see some of these kind of bigger projects, continuing to come out of the ground that are impactful from kind of a water conservation, water, sustainability side of things. But if done right, will also really be able to create meaningful kind of habitat in outdoor areas.
Great. So I'm going to give you 40 seconds to answer a combined one that goes zooming back in. And as we are getting, we know that a lot of cities are trying to look at using gray water, recycled water. Is there a trend to move away from the use of potable for toilets? And maybe that is both on the city and infrastructure side. And there has been, we talked about this too, for our project, keeping the aging infrastructure and the new fixtures that are out there in terms of low flow. And when you have a Blackwater, is there a conflict of interest, if you will, with low flow fixtures and aging infrastructure and using less water but needing a continual flow? So I'm trying to combine a few of those, but any trends that you're seeing?
I mean, I think what we've seen is more and more use of recycled water for flushing toilets in commercial projects, or tower, kind of larger projects, not on the residential, smaller scale, right? Not the single family home scale. I think that has a ways to go, but on kind of larger multifamily, residential, larger commercial, obviously academic, like at at Cal, there's a lot of opportunity for for dual plumbing and reuse. And then on the question regarding the infrastructure, when you have less water in a system that's relied on it over time, you have less flow to push kind of solids and toilet paper and whatnot down the sewer, and that can lead to problems. So you can't dry out your sewer. That'll lead to maintenance issues and potentially odor issues. So you do have to take into account, again, where you sit within a sewer shed, and how that sewer shed functions. The other element related to that is we have seen challenges in new buildings with projects not using the right types of gaskets and flush fixtures, and then recycled water that's kind of laden with salt, if you will, ruining said gaskets and causing a lot of repair costs. So knowing your water quality and what you're dealing with up front is critical. And if you are dealing with the recycled water, you really need to understand the quality of that water, and not make assumptions that you can just specify plumbing fixtures like you would if you were flushing with potable water. So I think the industry's learned a lot about that over the last 5 years.
Yeah, absolutely. John, it is clear that we need more time with expertise and inspirational folks like you. You have lots of love in the chat, so I hope you get to see that, with the appreciation for your and generosity of sharing out all that data. And we have, I'm sure, more questions for you for another time. But thank you again for making our work better, making our profession better, and all that you're doing to help us find wonderful, resilient solutions. So thank you to everyone who stayed on. I think that people would stay on for another hour if they could spend that time talking to you, but maybe Frank, Sarah, and Bill will find another moment to have a fireside chat with you.
Call me anytime. There you go.
Thank you, everybody.
Okay, thanks all. Really appreciate it. Bye now.
Good job, Lon. Good job, Pauline.
You're a good teacher, Frank.
Thanks, Frank.